Welcome
Hi,
back,
Gary.
everyone. Hi, Yunjin. We have Yunjin with us. You want to introduce yourself briefly to everyone? This is your first
Okay.
appearance this week.
Hi, everyone. I'm Yunjun Zhang. I'm right now a professor at the Chinese Academy of Sciences. Before I come here, I was in the US for a long time. I got my PhD at the University of Miami, then did a postdoc at Caltech. During my all time, I worked a lot on the NISAR mission, also mostly on the software side, together with my advisors and. I used to be a student at this course as well when I first started my PhD about 12 years ago. And my interest is on the InSAR time series. And right now I'm also working on the SAR system design and its applications in landslides and geohazards.
And Yunjin is going to lead us through some new material, new for this course and new to many of us, on processing Sentinel-1 data using ICE3. And the floor is yours.
Okay, let me share my screen. Let me see if I can hide this. Is now the site good?
Yep, I think
Yeah,
that looks good.
maybe I
Looks
would
good.
advise everyone to delete the folder and refresh just to make sure they get the most recent version of the notebooks because I've been having problems with that.
Right. Delete your notebook repository and then refresh it because I just updated the notebook about 10 hours or 12 hours ago, so it's relatively new.
Do you want to
You
show how you
need,
do that? You
Yeah,
could
can
double
you walk
click on
them
that
through it?
that repository there and then right click on the folder. No, don't
Okay.
delete the whole thing. You can just delete the folder with the notebook in it.
Right here,
Yeah,
you can delete this
delete.
notebook.
Yeah,
I'm going to do it and
and then click update repositories.
click update repository where here, right?
Yeah.
Okay.
We have a hand up. You have a quick question?
yeah, I have a small question. Like I did the git pull so that it can automatically updates in the terminal. So will it update or I need to delete it and then update?
This is basically doing a git pull. What
Yeah, this
you
button that
just
says
done.
like update repository is doing a git pull. I would do what Yunjin just did, delete the folder and then click on that button that he showed on the top of the screen that says update repository. It should be, if you haven't touched the notebook, it should replace it fine, but to be absolutely sure, delete the folder 2.1 ICE3 TOPS processing, and then update the repository. That's the surefire thing that you have the latest version of the notebook available.
And you may also need to check to make sure you have the right kernel selected for that notebook. Or it should be
Right.
set to Earthscope InSAR.
The kernel here.
Yes,
You should make sure you select the Earth scope InSAR here so that you can have so that you have all the dependencies installed. Okay, I assume most of you has done all that, and let's start with the notebook. So this is actually the first year we start to show the data processing with ICE3. It's the next generation of ICE2, which many of you may have seen it in the previous year's recordings. ICE3 is not a major update. It's actually an entire rewrite of ICE3 from the ICE2. So it get rid of many of those old Fortran code and rewrite many of those core modules in C and wrap them in Python. and it's also much more modern in the software architecture. So right now is designed to serve the processing purpose for NISAR, but the core module is generic for many sensors. And there's another project from JPL called OPERA, which um, which is developing that North America displacement products for all Sentinel-1 and NISAR data. And in that project, they developed several packages on top of ISCE to process Sentinel-1, and one of them is called Compass, which is used ISCE core module to do the co-registration of Sentinel-1 TOPS data. And that is what we are using it today mainly. And before we start, I want to acknowledge the work from Zhenli Tang, a PhD student working with me at Chinese Academy of Sciences, where he wrote most of the notebook today. And he's also in attendance list to answer questions if people have. So today's goal is to understand the unique features of the Sentinel-1 SAR data, including the TOPS mode, its specialty, and the new thing called the burst ID, which is the basic unit that we will use to do the new processing, and then we will use ISCE and Compass to generate an InSAR product, which will be equivalent to the TOPS app that we were using before for ISCE2, and we'll try to understand the various processing steps needed to generate these geocoded interferograms and try to visualize the intermediate and final results. So it mainly includes these few steps. And the core thing is after just three. First is to download the SAR data and then co-register them into the geocoded SRC, and then finally generate the interferograms from the geocoded SRC and do the burst stitching and phase unwrapping. And we can save the output into physical files because everything, especially the section 5 is all done in memory, so we did not write any files in the disk. So it's actually pretty efficient. So let's first start. To click the first cell to run. In the first cell, if you run it, eventually it will show some printout message like here. And you can see that in the folder, we'll generate the data folder and generate another folder called this. This is our working directory for this interferogram processing. And let me explain this cell before we import a few modules that we needed. The few core one is called Snafu. This is the Snafu developed by Stanford, and we're actually importing the Python wrapper of the Snafu, which is available on GitHub and the Conda Forge as well. And we are using Compass. And Zhenli and I wrote some utility scripts to help this notebook to run smoothly. So for us, for we to run InSAR pair, there's few parameters we need to set beforehand. First is these two dates. They set the reference and secondary date, and a bounding box in the west, south, east, and north in latitude and longitude. If you want to check, these are the corresponding polygons in the WKT format for us to search in the ASF afterwards. And the second part configuration is actually only these two parameters, which are the number of looks in the range and azimuth directions and the filtering strengths where we will do the interferometric processing, and all the other parameters are basically our standards that you actually don't need to change if you process your own interferograms. And okay, so let's see the folder inside. We create a few other folders inside. These are all right now are all empty. to store the data and auxiliary informations, the SLC to download the. Okay, let me before we do that. So SLC and orbits are self-explanatory. The TEC is called the total electronic content. These are to store the ionospheric data, the interferogram, which is the final product. The CSLC is called the co-registered SLC. So these are the output from the co-registration. So let's before we go through this, let's go the afterwards to the next cell to run first, and then we can explain the things backwards a little bit. Let's run this first cell. This is to download. Oh, it's pretty fast. This is download the burst ID. I will explain in a few seconds. And then let's run the next cell, which is to download the Sentinel-1 SLC data. This will uh, takes us maybe like 1 or 2 minutes. It's pretty fast. After you run this, let's go upwards to the beginning. So Sentinel-1, many of you may be already familiar. I will just go this part relatively quickly. Is the SAR satellite developed by ESA, and right now is actually the biggest. Is really a game changer. It's the first satellite that do the systematic imaging of the entire globe, land, and so it is from Sentinel-1 that we have all that we can do InSAR in almost anywhere on Earth. Um, and Sentinel-1 is using this specialized mode called TOPS mode. What it does is similar to a ScanSAR mode, but in each of the scan, it's rotating the radar beam from the backward to the forward while it flies. So as you can see from this figure, and because these are forward pointing along the track direction, this will introduce a few extra processing that we need during our INSAR processing, but this part has already been done relatively maturely in ISCE2 and also in ISCE3. And because of this, the basic unit of the imaging for Sentinel-1 is actually what they call this burst. This one thing that the radar beam is rotating from backward to the forward. This small field part is forming a burst, what we call it. And this burst is about 20 kilometers in length and about 90 kilometers in wide, and they're overlapping by 2 kilometers along the track direction, as you can see from here. So even though eventually we see an image look like this, the basic imaging unit for Sentinel-1 is actually split it into these few bursts. And since a few years ago, ESA published a new thing called the burst ID. They basically flagged each of the bursts with a unique ID through time. So the ID is stable through time, and each burst ID can be has you can imagine has this the this burst ID is a formula look like this. There are three components. One is the relative orbit. One is the burst index. One is the burst index describing the burst along this same track from all the way from the ascending node time. And the last one is the subswath. So by using these three number or stream, we can uniquely identify a unique burst globally. And this is one of the examples from generated by Sun from JPL used in the OPERA project. So you can see for example, here, the San Diego burst, which is the San Diego is covered by one Sentinel-1 burst, and we have the burst ID. And with each burst ID, we can assign a EPSG code, and we have a lat long bounding box here in the UTM coordinate. And we can have that for almost everywhere on Earth. And the exact number, exact calculation for the burst ID is look like this. The relative orbit and substrates are self-explanatory, and the burst index is essentially just computing from the orbital timing parameters, and all the way from the ascending node time, which is basically the when a new orbit when a new orbit started for Sentinel-1 satellite. That is the time when the satellite is moving from south to north across the equator. For the more information, if you want, you can check the website on the Sentinel-1 products, which is provided. Okay, that is about the SARS, that is about Sentinel-1. And for this notebook, these are the core dependencies that we're using. ISCE for the InSAR core module, Compass, which is calling ISCE to do the core registration, snafu for face unwrapping. Burst to Safe is a package developed by Forrest Williams from used to be in SF for the data downloading. EOF and SARDEM are developed by Scott Stanwitz for the orbit and DEM downloading, and GDAL for the burst stitching. I want to say a few more words on the burst to safe. This is what we're using right now. Is because the burst to safe is very helpful in the sense that when we used the ISA is still developed, ISA is still releasing all the SAR data in the entire frame or entire what they call the save file, and this save file usually includes about 27 bursts, as you can see from here. So each file is about 4 gigabytes in size, which is relatively large. And for us, since we can, since the burst from the Sentinel-1 is aligned almost perfectly through time, so we can actually process each of the bursts independently and download each of them independently, especially if you're processing only a small area of interest. And the burst to save library allows us to download each of the bursts independently and then pack them into the same save format as you can see, as you would expect from the official distribution, which is this is all made available through that package and through ASF, and that is what we're using. And for this and for this navigation, we also need a burst ID for Sentinel-1. And here we're using one burst ID database that is pre-built by the OPERA project, and that is available on GitHub as well. And that is what we're using right now. So to search the dataset, many of you may already did that. Here I will just do a very quick demo. So when we try to search the burst ID, we have the area of interest, which is around here I defined in this format. I just copy it over. Let me just do it with my keyboard. Search it here, and in the dataset, if you choose search burst, this will exactly shows where the burst is, where your ever interest is, and you can. Let me just do a search here. So we're choosing the Hawaii Big Island as an example here, including mainly the Kilauea volcano, which is around here. If we filter that with the direction, let's say you see here, if we're using ascending.
Yunjin, there is a question about the burst database. Is the Opera burst database global, or does it just cover North America?
It's global. So if you see each of these bursts, if you click one of them, for example, here, if you so from this searching, we can see we have 7 bursts covering covering our area of interest. If we click each one of them, you can see the burst ID here. You can see the relative orbit here, and the subsource, which is IW2, the second subsource. Yeah, so that's basically you can see visually where your bursts are on the SF website. And once you do that, let me go to here. Once you do that, you will get the path, you will get the subsource, and you can feed that into the burst to stack, which is an executable script from the burst to save package that we just mentioned. And you set up like this, including the relative orbit, including all the annotations, using the VV as the polarization, so you don't download the VH polarization data. And I use two subsources with the start date and the end date, the extent, which is the bounding box, and then you set up and then you specify an output directory, which will download all the data to. So you can see it found 7 bursts for the first date and 7 bursts for the second date, and then we packed all the 7 dates, packed all the 7 bursts into one save files, as you can see from here. So these are our just downloaded save files. So it will look like the same as that. It will look like the same as that official downloaded files from ISCE, but it's actually much smaller. You can see it's downloading that pretty fast. Okay, and the next is to download the precise orbit. Let's just execute the cell. It's downloading that again from ASF. And then we can download the DEM. Here, the DEM, I use a slightly bigger area of interest so that I can cover the areas from all the bursts, because because our downloaded burst, you can see our downloaded burst is covering a much bigger area than our specified area of interest. So I'm using a slightly bigger window if you see my cursors on the screen. This one is downloading the Copernicus DEM, which is using the data from the Tandem-X, the German solar satellite with the bistatic interferometry to generate generated a global high quality DEM, and the ones that we downloaded are the public 30 meters resolution DEMs. And we're also downloading a water mask from the NASA DEM, which is a latest version of that Sentinel of the SRTM mission, data reprocessed with the latest algorithms by NASA. And we're using the water mask from that database. This part is because for the ocean, this part is for the ocean. There's no valid SRTM data products, so it's not found, and that part will be set into the 0 or 1 depending on what you specify for the water body automatically by the software. So you don't need to worry. This is normal. Okay, with this finished, you can see from the folder that's in here, the DEM. We have the Copernicus DEM downloaded in GOT format, and we have the water body here. Okay, let's go to the next one. We're downloading the ionosphere as well, and more specifically, we're downloading the global ionospheric map product, or GIM or GIM products. This one we're downloading that because we're using the ionosphere for the co-registration also. In the next cell, I will spend a lot of time to explaining why we're doing that. And this one is downloading automatically from NASA Earth data. If you, I believe if you have your netrc file set it up, it will download automatically. If you have problems, please let me know. Most likely would be that you haven't select or agree or clicked on some data agreements. You can see it's downloading pretty fast. So let's go to the next. After we finish the data downloading, we can start to do the call registration. Let's run the next cells first. This cell is calling Compass to generate the configuration files in the YAML format. And let's run the next one as well. So it's now co-registering. So it's now generating the co-registered SLCs, the 14 bursts that we just downloading, using 4 workers in parallel to speed up. Okay, since if you are running that, let's go up to explain what we're doing. Here we're using Compass. This is similar to the ISCE2's tops up the PY. In ISCE2 we do the configuration in XML format file, but in Compass we're using a YAML instead, which to me is more user friendly. And below is a complete form of that configuration file, and let's go through that. So this first one is the processor that we're using here. We're generating the co-registered SLC for Sentinel-1. And then these few parts are just the inputs that we need to give, including the SLC file path, the orbit file path, the burst ID, the DEM file, the text file, or the ionospheric file, and the burst database file. So we basically just need to add the file path to these YAML files. And these are the scratch or the temporary file for the data processing. These are the products paths, the output paths for our CSLC. And here we're using the co-polarization data, the VV, for the co-registration. And during the geocoding, we do the flattening phase compensation, or we remove the phase contributions from the Earth's curvature and also from the topography. And the output SLC is 5 meters in X or 5 meters in longitude and 10 meters in latitude directions. These few are just the parameter in the intermediate parameters used to do in the geo to RDR processing. And we do correct for the timings for various timing corrections. And these are specifying the intermediate resolutions for the timing corrections. And in the range direction is in meters, and in azimuth directions is in the unit of seconds. These are usually not important. You don't need to change it. And here we also include the wet and dry tropospheric correction in the timing corrections. I will explain what timing corrections is afterwards also. And this part are also, you don't need to change anything here, except sometimes you may, if you want to output the latitude, longitude, and height for each of the pixel, you can do that. But here, since we are generating the geocoded SLC, everything is already in latitude and longitude, so you don't need that. Here is generating the loss directions, the ground to satellite line of sight vectors in the unit vector format. Yeah, so that's basically this. The afterwards are also standard. You don't need to change that. The output here is complex 42, complex 46. So what we're doing here is giving the downloaded save files. We find the available burst IDs that is suitable for InSAR. Basically, we have all the bursts that has multiple dates. And for each of the bursts, we search in our directory the available given the name patterns, we can locate each of the exact file paths for the SLC, for the orbit, and for the ionosphere, and then we can write that into the YAML files. And within here, within these functions, if you're interested, you can look at the. If you're interested, but currently it's pretty long. If you're interested, you can take a look here. But eventually, this one is. Let me just do a search. So this one is basically putting all the paths into the complete YAML file that we just showed and write it into a YAML file. So the output is here in the data directory in here and in C run config. These are the YAML files that we wrote. And I believe right now we're almost finishing the co-registration. This part is pretty fast. It's because we speed it up. We speed up the processing a little bit. We reduced the output SLC resolution from 5 by 10 meters default one to 10 by 20 meters instead, so that the whole processing can be more can be faster. But if you're processing your own, you don't need to change that. You can change it back to 5 and 10 or just remove this part. So what does is in this so what does here is co-register each SLCs independently from the radar coordinate into a common geographic coordinate, which is really the new things which is really the new thing and very different from ISCE2, and I'll explain why we're doing that. So you can see here is very fast because we're having 14 bursts and we're finishing that in about 6 minutes. So that's like half minutes, one burst. And the file is here organized with the burst IDs, and each burst ID have a date. And we have the SLCs in the H5 format. I will explain the file format also momentarily. Here is the quick overview of that SLCs that we just generated already in the GSF, already in geocoded coordinates. So why we can do this? This is all because this is actually all because a few work that we have achieved as a community in the last few years. One core thing is the geocoded SLC that proposed by Professor Howard Zebaker in Stanford. That he proposed that we can actually do the InSAR processing in that we can use the geocoded SLCs before we do the co-registration or before we do the interferometry. And that is really new and it makes the whole thing much more easy. And another thing is that the geolocation accuracy for InSAR, for SAR satellite, is now much better understood as a community. This is because when we do the co-registration, we'll really just align two SLCs into a common coordinates, either in radar or geo coordinate. And the accuracy of the alignment is required for InSAR because for us to form a coherent phase to do a successful interferometry, the co-registration accuracy needs to be less than 0.1 pixel. And for 0.1 pixel for Sentinel-1 is the slant range the resolution in slant range is 2.3 meters and in azimuth is 14.1 meters. So 0.1 is actually about 20 centimeters in range and 1.4 meters in azimuth. And through a few papers that our community has, including mine, we can now see that actually for Sentinel-1, the range geolocation accuracy now actually can achieve at the level of 5 to 6 centimeters as 1 sigma. So we can actually achieve the 23 centimeters of the co-registration threshold by more than 4 sigmas, which is really reliable, and that makes the geocoding for each SLC into geocoordinate very accurate and accurate enough for interferometry. And of course, that is accurate enough for other SAR time series analysis if you're doing not just InSAR, right? And this whole thing behind is the geolocation theory, which is what I'm trying to show here. These are the satellite flying along this direction, and we have the target around here. The dashed lines are the ellipsoid of the Earth. The solid lines are the actual DEM or DSN of the ground. So when we're doing the imagings, the entire geometry, including the velocity and the position of the satellite and the position of the target on the ground, can be described by these range Doppler equations shown on the right. Here the T is for target on the ground. The R is the position. The V is the velocity. Both are the vectors. And the lambda is the radar wavelength. R is the slant range distance. The FDC is the range Doppler frequency that is the Doppler centroid, and the given azimuth time or the slow time, and the slant range or the fast time. And for a satellite, we know the T, we know the tau, we know the FDC, and we know the R. And given from the precise orbit, we know the VS and the RS as well. So all we're trying to resolve or from these equations is the RT, which is composed of the X, Y, and the height. And the height can be this, if we know the X and Y, the height we can interpolate it from an existing DEM. So the VS and RS from the precise orbits, DEM we can get already globally. So with these two equations, we only have two parameters to solve, which is the X and Y. And so through these equations, we can establish the relationship between the South satellite and between the radar coordinate and the geo coordinate for each pixel or each target on the ground. And eventually, these are the ideal case, which only includes the geometry, but actually it's not exactly that. This is because when the radar echoes is propagating through the atmosphere, we will have the atmospheric delay, not just for INSAR, for the radar wave, for the time delay also. So this is not just the spatially relative delay. We have the entire bulk delay for the entire image as well, right? And that bulk delay from the ionosphere, from the troposphere, and also our Earth is not entirely stable. Our Earth is having all types of the plate motion, the solid Earth tides, the ocean tidal loading, all that effects will change the positions of the target on the ground as well. So we need to besides this pure geometrical information, we also need to account for the atmospheric delay and ground motions, so that we can achieve a very precise relationship between the radar and the geo coordinate. And that is the core thing for this new processing workflow. And now let me try to. Yeah, so the workflow is explained as these few steps. Once we have the XY, we can convert that into the Earth center, Earth fixed coordinate using the DEM, and then we can solve the range Doppler equations above to get the T and tau, and then we can apply the timing corrections to the T and tau, which is the range and azimuth timing or range and azimuth distance. And then we can interpolate that into the SAR, into the radar SLCs at the correct positions, and then we can form and we can solve this equation iteratively so that we can achieve a very precise accuracy, because this whole equation is not linear. And then at the end, once we are happy with the precision that we got from the X and Y, we can get the accurate distance from the R, and we can remove that and then we can remove that phase, which essentially, this R essentially includes the phase from the Earth's curvature and topography, and we can remove that from the SLC so that our SLC's face is already flattened, and we can form an interferometry easily afterwards. And that is the work done by Zheng Yujie, which is now a professor at UT Dallas. The entire workflow and algorithms of this new GSOC co-registration, you can find that in the OPERA S1 CSOC algorithm theoretical basis document online, which is now already public. If you click the link here, which will show you the exact equation, the exact algorithms that we're using. So this new workflow is very convenient because of a few reasons, and one of the biggest reasons for me is that it's co-register each SLC independently. What we mean is, before in ISCE2, we are co-register one SLC or the secondary SLC into a reference SLC using two steps. We first are using the precise orbits and DEM to do the geometrical co-registration, which is basically solving this equation here. And laterwards, for this atmospheric delay and ground motion, this extra time delay stuff, we're not really solving that using exact math and physics behind, but using a data-driven approach such as cross-correlation or enhanced spectral diversity, which can estimate the bulk delay or the bulk offset in range and azimuth directions between the two SLCs. So when we do that, we're basically aligning one SLCs into another one, which is a relative alignment. And since we now know the physical processes behind it now much better, we can use physical models to calculate this using external data set without any data-driven refinement. So by doing that, we are not really aligning each SLCs into another one, but we are aligning all the SLCs into a common geophysical grid. And that makes the whole things much easier, so much more independently. And then if you think, you can imagine that if you are doing processing like this, assuming the accuracy is enough, when we do the updating, you can just store all the GSLC or the CSLCs in the same file, and so your what I'm saying is, so your time series updating will be much easier when you co-register in this approach. Let me see if people have questions about this. I actually cannot see it from your. If you have questions, please speak up.
Yeah, we went through and answered most.
Okay.
But we've been answering them by online.
Great, thank you. So the output of this is a CSOC in the HDF5 format. The HDF5 format is a hierarchical format, and the basic structure look like this. We have some metadata in the root level. We have some quality assurance metadata also in the root level, and some identification. And the key data sets are here. The first one is the VV polarized co-registered SRC in the complex 46 format, and we have a few others which are including the X coordinate, the Y coordinate, which is a 1D matrix. And then we have a few timing corrections, including the slant range, the zero Doppler, the bistatic delay, and this other stuff. I will explain right now what are they. Before that, I assume most of us have already finished the co-registration. Mine already finished here long ago. So we can just plot the results here by running this cell. Here we just plot, even though we have 14 bursts, here we just plot one burst as a demonstration, which is this one here at this stage. And these are the input, which is the downloaded SRC burst in the radar coordinate. And these are the geo coordinate from here. Okay. And you can see the nice thing is this is already rotated, so everything is already in geo coordinate, in the UTM coordinate, more specifically. Okay, now after that, let's see what exactly we're doing here. The equations is on the equations is here, and the precise orbit and DM are already very accurate. Especially the precise orbit is already very accurate for Sentinel-1. Is in the level of 1 to 3 centimeters, which is really precise. And for DEM, even though it's not very accurate in the mountains regions, but it does not really affect the relative alignment between the SRCs. So it is fine for the co-registration purpose. And the unknown part is actually the atmospheric delay and the ground motions that we used to not notice so well. And that is what we're showing here in the 4.3 sessions. And for this part, we mainly includes 3 parts. We mainly includes 2 categories. Actually, one is the what we call the physical timing delays, including the ionosphere, the troposphere, the solid Earth tide, and the solid Earth tides in both line of sight directions and the range directions and the azimuth directions. And besides that, there's also actually some focusing artifacts which now we also know better through many studies done by ISCE, especially the DLR teams, where they find when ISCE doing the image focusing for the Sentinel-1 SRC for the Sentinel-1 SAR data. They used several assumptions which makes the whole thing much faster, but that actually can introduce several artifacts including some delays in both range and azimuth directions, and that can affect our geolocation accuracy and also our co-registration accuracy as well. So let's first see what are they. Let's run this first. Let's run this cell and see what are they. These parts most of them are already included in the H5 file that we just generated because it's used in our co-registration. This part is the ionospheric delay in the range directions in the very coarse resolution, about 120 meters in range and a few fraction of seconds in the azimuth directions, and we are generating that using the standard atmospheric delay formulas. And our input file is that global atmospheric maps that we just downloaded in this 3.4 session. The second one is the static tropospheric delay, including the wet and dry delay. This part is actually generated through an equation here. This equation, what I first saw is actually from a paper by DLR, which they use the same equation for the Terrace X processing. And here the ZTD is a fixed tropospheric delay. I think it's about 2.3 meters representing a typical tropospheric delay in the equator region at the mean sea level, and then we can adjust that for all the different heights, and then project that into the radar line of sight directions so that we can get a very fast tropospheric delay because the equation is the same, even though you can see it's very simple. Does not grab all the information, but it can actually get the bulk tropospheric delay relatively well. And the most important thing is there's no latency for this part, because when we do the co-registration, we especially for some processing data for OPERA, like we have a latency requirement. We want to do all of that almost immediately. And for ERA5 and other global atmospheric models, we can also get this more precisely, but that one has usually a latency at least 3 to 5 days, which is not fast enough for us.
Yunjin, I
Yeah.
note that we are getting close to 11:50 Pacific.
Okay.
So we can take a break once you find a good natural spot to do so.
Right. Okay. We'll finish right after here. Yeah.
There was one question in the Q&A. Are the ISA ETAD corrections used in the compass processing?
Equivalently, yes. The ETAD or the ETAD is including almost the same component as this, but we're not exactly using that ETAD products. Is because first the ETAD products, I believe, is not releasing that for the historic data set. And we do in the Compass, or actually in the S1 Reader, which is another project, another package that Compass is calling. That one includes all the equations. So including all the equations, we basically just we basically just implement that algorithms very faithfully, following their own ATBD or the algorithm document. So this is equivalent to ETAD, but we're not exactly using that product. We're using our own code to generate that. The later two are the solid Earth tide in the range direction, in the azimuth direction. The focusing artifacts, you can find more very detailed explanations on these artifacts in the Gissinger's paper. If you click it, it will bring you to there. And this is what it looks like. So you can see all these are in the unit are in the unit of pixels. You can see these are the Doppler induced range shift in the pixel, which is really small. The bystack delay in the range direction, which is also is relatively large, but it's still very small. And the azimuth FM rate mismatch is also relatively small. So these things used to be not accounted for in our InSAR processing, but because their impact are actually relatively minimum, especially actually if we do the InSAR, we're basically doing the relative in time. Their time variation of this is even smaller, but this part is actually important for the geolocation or for the co-registration. So we are implementing that for all the bursts when we co-register using Compass. Yeah, so from this, which is, let's go back. From this, which is essentially this one script, we are doing the co-registration to co-register each of the SLC burst from radar directly into geo-coordinate, and assure all the geo-coordinate, and assure all of them are already aligned perfectly for the InSAR, for the interferometric processing afterwards. And that's what we were demonstrating in the next session. So we can take a break now.
Yeah, how about 10 minutes? Does that sound good?
Sounds good.
Melissa, could you do the honors?
Yep, just getting there.
Great, thanks.
Thanks for all the questions. We'll be back shortly.
Okay. Let's
Let's see some
start.
interferograms.
Yeah. Let's see. You can see my screen.
Yes.
Great, thank you. So now since we just had already those geocoded, co-registered SLCs, we said it was aligned perfectly for interferometry, and we also said it was the phase from the Earth's curvature and from topography has already been removed. So in theory, we can just do the simple conjugate multiplication to form the interferogram like the equations here, right? And that is what we're trying to do. So the following on, we're just doing the interferometry processing for those geocoded bursts. And we will first form the burst interferograms, and we can generate two products from that. One is the interferogram itself, the other is the spatial coherence by using the equations here, which many of us already should have already learned these basic equations. And let's just run the cells below. This is doing exactly that. So you can see here, except this part where we're using some functions to read the H5 files. All the rest are using basic Pythons, and we're just using one burst ID, one burst for demonstration. Here we are reading those SLCs here in the complex 46 format. And now we're just forming the interferogram look like this. Just two complex numbers doing the conjugate multiplication, and here we're masking the pixels with zero magnitude of the interferograms. Basically, those invalid pixels into nums, so it's helpful in the plotting. The next few cells are just a faithful implementation of the equations above, but we're doing that in a slightly faster version using the convolution functions here, which is calling the SciPy for a faster implementation. And if you run the next cell, it'll plot that. These are the two burst interferograms we just formed. One is the phase part, one is the spatial coherence, and here are the Mauna craters right here. And we have those rift zones here alongside here. This part are the invalid areas we have in our geo coordinate. These parts are water, so they are relatively low in coherence. But this part, since here we have the coastlines and coherence, but this part is slightly low coherence because of vegetation. This part is also because of the vegetation. And the entire products is already in the UTM coordinate. And we can do the same thing for all bursts, and we can do it just right here. This function just pack the package, just pack the few code above into a function, so we can do them in a for loop relatively easily. So you can see it's doing that really fast. We can form interferograms momentarily. And this here, we're writing each of the burst interferograms and coherence into a GeoTIFF file. And then we can just stitch them because they're already geocoded. So we can just use GDAL, which is what we're calling inside these functions to geocode each one of them. And done. And now we can just plot the output. Here we are using we are feeding those burst interference paths into it, and then we are specifying a bounding box so that we can only get our input out our area of interest, and this is what it looks like. The interferograms, the phase, and the coherence. Here the clear creator is right here. Here are the rift zones, and here I believe is the new. These few are the new lava flows, if I remember right, and these are the old lava flows which are now already covered partially by vegetation. So there's a few. So they are low coherence. Did everyone get it here? Could you say that in your in the chat? Do we know everyone is catching up? Oh, we don't have that function here.
Are you seeing all the thumbs ups, right?
Great.
Cascading
Great.
across the screen. There's lots of
Great.
them.
So you can see that through this very simple approach, we can actually form a valid interferogram, right? And here this relatively noisy because here we're doing that in relatively full resolution. Note that here when we generate the SLCs, we reduce the resolution twice by 2 times to speed up. But if you're doing the full resolution, it will be similar look like this. And now, usually we don't need that high resolution for many applications. So we can do a multi-looking to increase the signal to noise ratio and to do a filtering, mostly the gold stain filtering to further increase the signal to noise ratio, which is again really fast. And then we just plot the results. Here we did an extra 4x2 looks in range and azimuth direction, so we can have a relatively square shape like pixels in the output, and we're applying a gold stain filter with strength of 0.5. And these are the result, the original full resolution. The multi-looked ones, you can see the size here is already shrinked. Once we do the filtering, the face quality is already increased much better. And after we do a filtering, it's increased even better. And we do a filtering here because the Sentinel-1 C band data is has relatively low coherence in the vegetated areas. I believe we have seen some preliminary NISAR data where we have 12 days interferograms, L band, the coherence. I heard is so good that we don't need to do the filtering anymore, which is really amazing. And another thing is we have that complex coherence above, which is generated from the SLC. Using the equations here, and when we in ISCE2, we also have another coherence. It's actually called phase sigma, or I call it the phase sigma coherence, which is defined here. This is not exactly the standard coherence because what it does is generate purely from the interferometric phase itself. It's calculating the phase standard deviation, which is the sigma phi here, and then converted that into a coherence using the equation here, where the NLK is the number of looks applied during the processing. And this one is actually, I found it also really helpful in many ways. We're now just estimating that, and let's just first see how it looks like. This one is the standard coherence. This one is a phase sigma coherence purely from the phase. So the left one is calculated from SLCs, and the right one is calculated from the interferogram, especially the phase itself. So after we do the filtering, after we do the multi-looking and interferometric filtering, you can see the phase quality got significantly better, right? And in that case, I find the phase sigma coherence can better characterize the phase quality itself because it captures the impact from the effect from the filtering. But here, but here usually is usually used more, I believe, in the damped proxy maps where they use coherence as a change detection to detect the damage on the ground. And the standard algorithm is using this one as the input, as the basis. And in
There was
reality,
Before we
yeah,
go a bit further ahead, there was a question about how the stitching was implemented and what happens to the burst overlaps in the stitching.
right. That's a good question. So what we're doing here is we're not stitching the SRCs first. We are actually forming the burst interferogram and stitch the burst interferograms. This is because I know this is not a question, but I think this is also important. So let me explain that. It's because in the burst overlap, if we're stitching, so when we do the stitch, we are literally just overlapping the older or the newer burst onto the old burst. So the burst overlap areas will be just override by the newer burst. And that is done for within the entire subswaths. And between subswaths, the subswath 2 will override subswath 1, subswath 3 will override subswath 2. So it's simply as that. That is also what we were using in ICE2. And
Yunjun, the
yeah,
coherence had some lines on there. If you can go a little bit down there, could that be
I
related
thought
to stitching? Hello.
yes, yes. No, this is not. This because you can see from the coherence, it's fine. From the standard coherence, it's fine. From here, this is because of the ionosphere. Let me,
Are
if
you
you
sure
zoom,
it's not because of it's a moving window, and so it'll be different at the edges of the burst?
yeah. Oh, you think it's? I thought it was because of this. This
Oh, yeah, yeah, yeah. No, that's
yeah.
yeah.
Right, this part is because this we are right now we are this is the SSC at 2024 August and September, and we find here this burst overlap should be because of the ionosphere, and so that include that introduced this phase jump between the bursts. And when we, as you said, when we're doing the windows to do the coherence estimation, we're using a 5 by 5 windows here also. That this phase jump introduced these lines.
Okay, thank you.
Yeah. So we go back, if we go back to the stitching, here we're stitching the interferograms. We're not stitching the SOCs because if you are because you can imagine, I actually cannot. Let me if I can draw here. Yeah, okay, I can draw here. If we have one SLC, one burst SLC here, and if we have another burst SLC here, and then the overlap is using this burst, and the next one, if we have another date, because the burst overlap are not perfectly right. Are not they are really great, but they're not perfectly. So the next time we have the burst overlap look like this, and then this part will be the same in the same date. But this part, if you see my screen, this part, the date will be, sorry, let me draw another one look like this. So let me see if I can redo it. Clear on my drawing. If you have one day look like this, another one look like this, the next date is here and here. So this part, we're always using the above ones, and here we are using the above ones. So then in this area, we are using, in this area, if you're doing interferometry, we're using the lower burst for the first date and the upper burst on the second date. That what makes the whole thing not exactly ideal. So for us to avoid that, we're doing the burst interference first, before we do the burst stitching. Yeah, did I answer your question? Okay, I will take that as a yes. So now we have this, and then we can just do the face unwrapping. And here we're using, let's run it first. Here we're using Snafu, and nicely JPL has released a Python version or Python wrapper of the standard Snafu. So we can now import it in pure Python, and that's what we did. That's what we did here, and we can call that using Python functions instead of the executables. And let's go back. So what we did here is these are the interference we have, and then we mask out the water areas to speed up. You don't have to do that. This is optional. And then we feed it into Snafu, and we give the phase, we give the interference, we give the phase sigma. These are what they call the effective number of looks, which is the number of looks we applied during the processing, but then I divided by 1.2 because this is the oversampling factor, typical oversampling factor we used for the self-focusing, because our pixel size is usually smaller than the resolution cells that we actually are. So if really the effective number of looks are like this, which is already commonly used in ISCE as well. Here are the few standard parameters in Snafu. Okay, so you can see it's finished also in less than 1 minute because our interference are relatively small. And let's see the result. So these are the wrapped interference. These are the unwrapped ones. We have the actually, if maybe Fog or Eric can help, what is exactly this part? I believe the event is there's an eruption on 2024 September 2024 on Kilauea.
I believe the magma chamber is under the summit caldera, and that's deflating whilst the rift zone is experiencing a dike intrusion.
Great. Thank you, Gareth. And besides this, there's also another byproduct called connected component, which is really useful. We'll see more of that actually in the last day during the time series analysis part. The connected component is generated by Snafu as well, and the dark blue regions are the background with a zero value, which usually represents the unreliable pixels identified or Snafu think. And the non-zero areas are Snafu think they can unwrap. And then in this case, we only have one very big areas with zero with a value of 1, which is really nice, which means Snafu thinks these areas are all relatively reliably unwrapped. And in other challenging cases, you might see multiple areas. There's another area isolated from this one, which usually labeled as 2 or 3 or higher numbers. Those are also can be unwrapped, but Snafu think they might have unwrapping errors between that areas and these and other areas. So kinetic component is basically a quality measurement for the phase unwrapping, which can help us to identify potential phase unwrapping errors. Okay, so we have all that, and now we can just save the processed results into the physical files, and we can use that for other interesting stuff like the modeling. And let's just run the next cell first. What this cell doing is it's preparing what they call the static layer. And the static layer means the layover shadow mask, local instance angles, and the loss vectors, basically the instance angle and azimuth angle of the loss vectors. These are not generated by default. in the compass processing, but they can be. And one lucky thing is that these static layers, they are not changing significantly in time. We can use the same static layers for all time series. And for OPERA, which basically includes the US territories, including the mainland Alaska and all the territories on the Pacific, the static layers are already generated and you can just download it directly from ASF, and that is what we're doing it here. And if your areas is not there, you can generate it using Compass as well by basically changing the executables from the CSC into the CSC static. This will generate, then you can run, and then you can run the Compass again, and this will generate the static layers for these specific burst IDs. And that's what we're doing here. We're trying to find for the given burst IDs. If they exist, we will just download it directly. If they're missing, we'll generate it using Compass. And luckily, we find all of them are available for this specific case. So they're really fast. And if you download that and if you generate that yourself, it takes a few minutes, but it's not really long. Then we can stitch those static layers like we did for the burst interferograms. So since here we are right now, I'm only interested in the loss vectors. So these the two data sets that I'm stitching, and these are the stitched results. They're again also already in the UTM coordinate. Here the loss azimuth angle is defined. Loss azimuth angle is defined as the vector of the target on the ground pointing towards the satellite, and starting from the north as 0 with positive along the anti-clockwise directions. So that's why for an ascending track, we have an azimuth angle look like this, and that's make it around 100 degrees. And we can write that into files. Here, the very simple one is just write that into a GeoTIFF, and that we can see it here, and that's what we generated here on the data sets. If we go to the folders in the interferograms, here are the burst interferograms that we generated, including the interferograms coherence, and here are the merged ones, including the unwrapped phase, the kinetic component, the phase sigma coherence, these are the wrapped interferograms and the loss vectors that we have. Yeah, so that's basically the end of the regular interferogram processing using the new I3 compass approach. Let's see if there's some questions.
There's lots of different questions. Some more directly relevant than others. There are some people asking for clarification on how the phase sigma coherence is estimated and what it means.
The phase sigma, let me go.
And what's the difference between that and say regular correlation, and why?
First, I don't think the end one sentence summary is the phase sigma coherence. I don't think the differences between that and the standard coherence are really well intensively studied or compared. I see different softwares has different of them. Even in ISCE2, the top stack and the strip map stack using the phase sigma, and the Elo stack is using the complex coherence. in gamma, in gamma processing, people they're using phase sigma coherence a lot, and some paper has shown that the phase sigma can be helpful in the phase unwrapping process because it represents directly the quality of the phase. You can see that from the equation itself. Phase sigma is exactly correlated with the standard deviation of the phase itself. And in practice, when it does, it will also notice this part. It will also remove actually a local gradient within this estimation window, so that you don't so that the phase quality does not so that the phase ramp does not affect the standard deviation calculation. Um, so one word, in a simple way, phase sigma is really just the phase sigma, just represents the variation of the interferometric phase. The standard coherence has the impact from both the phase and the magnitude. And the standard coherence, you cannot calculate that after filtering, right? Because it starts with SLCs. So for the filtered phase, I find the phase sigma looks to me more reasonable, but the standard coherence should also be very helpful. I don't think right now there's a consensus on which one is better or what. They're just two parameters out there. They're both calculated, and I don't see papers that really intensively compare or evaluate their differences.
Yeah, the big difference is the filtering. It's because after you do the Goldstein-Warner filter, you've done a nonlinear filtering of the phase, and it's no longer it's a different it's you're measuring something that's been changed a lot. I mean, for phase unwrapping, the filtered, you want to have a good estimate of what the phase quality is after filtering. But if you want to actually look at the coherence as a function of what's actually on the ground, you have to use the unfiltered coherence, like for damage mapping or other or studies of forest height or anything there where you need to know what the coherence is at a given location.
Sounds good to me as well. Yeah, as I said
Yeah,
that.
there's another question here about whether we can use the filtered phase sigma coherence for change detection. No, it's going to be very inaccurate for doing change detection because of that nonlinear filter that's been applied with the Goldstein-Warner filter.
Yeah,
It'll
there's
also be
really.
a bunch blurrier.
Mhm. Let's see here. Yeah, you can see on this part, after this part, the phase sigma is having a much higher value compared with the standard coherence. Okay, so let's move forward. The last two words I want to add is on the ionosphere correction. Right now, with the current tools we have, we cannot really easily do the ionosphere correction using the standard split spectrum method because we cannot really form we cannot really get the subband SLCs from the GSLCs, but you can form the subband SLCs before the co-registration, and then you can co-register the subband SLCs into subband GSLCs, and then form the interferogram and form the standard using that interferometric pairs to estimate that ionospheric delays using like the standard products. So if you do that, the only difference is you have to form the subband SLCs before the co-registration and then apply the same, almost exactly the same co-registration process to your subband SLCs. But that part is not exactly ready to the end users in the current status of the code. So yeah, so that's basically the status. And the earlier those phase jump that we have that we see earlier, that is actually we think that's the ionosphere as you can see it from here, and here those are the burst boundaries, and here are also another burst boundaries, and here, and that part is not always there because that depends on the ionospheric status, of course. And here is another pair, again on 2024, but in a different date, and we do exactly the same process, and we don't see those burst jumps here. So that's yeah. So that's basically that part on the ionospheric correction. And for the homework on this part, we would like you to process another Sentinel-1 interferogram for an earthquake. One choice would be the 2020 earthquake in Turkey. This is what you will use for the next session along with Gareth. And of course, you can also choose another earthquake or interest or another area of yours. That is also fine. The last words is on the OPERA. The OPERA project, besides generating those displacement products, you can see that from the ASF website. It also generates a level 2 intermediate product called the CSLC or the co-register SLC for all the Sentinel-1 SLCs in US territories and about 200 kilometers along the Canada, away from the US boundaries and all the way down to the Panama, if I'm right, yeah. So that's basically almost the entire North America continent. You have already those GSLCs, so you can skip the section 3 and then so you can skip the section 4 and directly go to section 5, which makes the whole thing there much easily. The last two parts are just naming conventions for those OPERA SLC products. They are named as this. You can find the burst ID, the dates, and the generation dates there. And the products look like this. And these are the relevant papers. If you're interested on the algorithms behind, let's see if there's still some questions, or you can go to the demo quickly on the stacking.
There's a question about the convention for the azimuth angle.
I believe it's the same. You answered, yeah, that's fine. Yeah, that's good. Yeah.
Yeah. It's in the Q&A if you want to look.
Yeah. Actually, for the damage proxy for the change detection, I am using also. I'm trying to use Phase Sigma as well. It's just I actually find it personally. I find it actually sometimes more accurate. Although we're still trying to find the reasons why or the physical meanings why is that. But that is still a very active area of research.
I think Scott Hensley's made the only paper I've seen where he attempted to make the probability and like the distributions you expect for the data after running the Goldstein filter. But it's a pretty
Oh.
complicated paper, so I gave up on it.
Great. Thank you, Scott.
Also, Amrit
Could you-
said the azimuth angle is weird, and I'll double check that what's active is similar, but I think you're right that it might be different in ICE3 than in ICE2, which is kind of
ICE2 was like big negative angles, which are
Yeah.
always like hard to interpret, but they were actually in a north. They were relative to north, but I don't know yet how it works in.
These ones I actually checked. It looks right to me. What's the
Okay. Oh, maybe it's the heading angle that's weird. That's like not actually the
yeah.
satellite.
The heading angle is different, right?
Yeah.
This is the loss vectors azimuth angle.
And is it pointing from for the ground to the satellite, which is what
Ground
the
to the
convention
satellite.
was in ICE2 as well.
Yeah, so I specifically make these two because these are the code that we adjusted a little bit. I specifically make it consistent with S2.
There's this question about sweets, Scott. I think that's one for you.
I don't know. I don't have. I guess I will. So Sweets is something I made 3 or 4 years ago before, like while Compass was in development. It is mostly still working. The active branch is pointing to a lot of my forks and branches because I don't have merge capabilities on a lot of the Opera projects and the ICE projects because they're like in active development. So I think we're still trying to figure out how to best handle that because I can't actively change the code either, and it's not used by anyone like on the NISAR project or anything or on the Opera project. So like people do find it useful, but it's in open source limbo. But to directly answer the question, yes, it does a lot of the stuff. I actually don't know if Engine might have added more corrections, but it's
I
very,
think
very similar.
I found the default compass was not using the ionosphere, so I just added that.
Yeah, that might be the one.
Yeah.
There's a question for Melissa. What happens to the Q&A text? Does it get saved and is it going to be shared?
It's being saved, and yes, it is shared on the Moodle.
There you go.
Okay, so let's go to the next one. If you go back to your repository on the 2.1, there's a stack folder. And if you click here, there's a burst stack notebook, which is slightly simpler. And in this one, Jen Lee and I are trying to demonstrate how to do the stack processing. And as you can imagine, with this new workflow, the stack processing is much more straightforward. The workflow is actually almost the same as the single infinitogram, except you're just repeating that in a stack version, in a stack fashion. Here, since the data set are relatively large, so I will just okay. I think it's the base. I'm not choosing it correctly. I will just run through that because I have already prepared some in advance so that we can save time on this live session. The data structure is almost the same as the pairs. If we run through that, most of the code is the same. Again, we're doing the exact same workflow. Let's see if it works. Let's see if it runs. Okay, we'll take some time. I'll just explain the content of the table. You can see is exactly the same, almost exactly the same steps that we have. Downloading all the SAR data, first preparing the burst ID database, which is shared actually across all your projects. So that's why I put that into a very common directories, and then you download the SRC data using the burst to stack, which is the burst to save package. And in there, you can directly specify the starting date and end date, and this will download your burst of interest with your time of your interest directly. Okay, it's working. So let's run the next one. And next one, this one is already exists because I share the same using the same one as previously. So it finds 27 bursts, which can include which will end up with 9 save files, and then download the orbits and DEM using the EOF, using Sentinel-1 EOF and SAR-DEM, and ionosphere, which is same as before, but we're doing that in a time series fashion. Given the SLC directory, we can grab all the date lists, and for each of the date, we download the text files, and then we can do the SLC call registration. And except this time, Compass has a script for that, for the stack call registration, which is this one. And this one is, let me see, the download may take some time. So this one is generating the configuration files and round files for the call registration itself. And for after that, since that by default it's not adding the atmospheric correction, and I find sometimes it's important, so I modify the generated YAML file, the configuration file, to include the atmospheric correction using these cells below. And after that, you will see a folder in here, the CSRC run config, which are the same thing as you see it from before. And along with that, there's a folder called run files. And in the run file, if you open it, you can see this is, if people are familiar with ISCE2, these are the functions like ISCE2. We're calling the S1 CSC.py again, with feeding that with a YAML file that we just saw. And you can do that and then you can basically just run each of the run files one by one, or do that in a HPC fashion or parallel fashion if you like. And after that, you can again prepare the static layers. And one last thing here is for time series analysis. For example, for MintPy, when we do the DM error correction, we need the perpendicular spatial baseline. So here there's a function to compute that and then save that in a TXT file so that it can be loaded into MintPy. And after that, you basically have all the things that you need to form the interferograms. And then in this case, all you need to do is to first crop your SRC, crop and stitch your SRC into your area of interest from those list of bursts, and then select the interferograms. Sorry, I don't think this is correct. We should just select the interferogram pairs. For example, like those S-bus small baseline network, or the sequential network, plus those annual pairs, those temporal baselines that is around 1 year apart. That is usually helpful if you're processing challenging areas. And then for each of the pairs, using the same approach that we did earlier to do the stitching, multi-looking, filtering, and phase unwrapping. And currently, I'm not going to show this part because this part will take quite a long time. And currently, for the 1 and 2, as Scott said earlier, you can use suites to do exactly 1 and 2. And for all that, I believe, except for the ionosphere, it's not included yet. And then for Swiss, if I remember correctly, after you do the stack SLC co-registration, you can feed it directly into Dolphin to do the face linking, which with Scott, I believe, will show that in the last day. And it does not right now in the Swiss does not include the SBAS approach yet, but we do plan to include that in MintPy. In the next version, we hope to support the GSLC stack directly as input to MintPy, and then you can do the stitching, the interferogram formation, filtering, and unwrapping all within MintPy. So that's basically it. And currently, we are still having an open PR, not merged yet, which supports the stack interferograms that is generated through this approach we showed here. But it's not merged yet. We're still doing the code cleaning, and hopefully in the next release. Okay, so this part is done. The next part will be the same, usually really fast. So let's see if the people having questions. So you can see here with the new approach, the stack processing is really straightforward, making the whole thing much easier.
There's a couple of questions in the Q&A about the TeX files, like what format they're in, and can you use them to correct the phase?
The INX format is called the IONX. If I type it on the screen, it's called IONX format, which is a standard ionospheric format in the ionospheric community. I think that's the slightly newer version of that, which is a global product in a very low resolution, and it represents or at least it assumes the vertical total electronic content, and assume that in a same shell at a height of 450 kilometers height. And we're using that just to do the atmospheric correction for co-registration. And because you can see earlier in the pairs notebook, we calculate the ionosphere, the troposphere, and the solid Earth tide, but their absolute value or their bulk value are actually more important than their spatial variation, because the bulk value are actually usually much higher than the variation itself. For troposphere, for example, the absolute tropospheric delay varies from 2 to 4 meters, but the temporal variation of the tropospheric delay is actually only within 25 centimeters. So that's why the low resolution of those ionospheric products does not affect the co-registration itself, because we don't need those, because for the co-registration purpose we don't need the spatial variations. And for the phase, it helps a little bit. I have actually a student working with me published a paper just this year on TGAS, where we evaluate the performance of different tech products for the phase corrections in a time series fashion, because we know because previously people had tested in the pairs, it does not work most of the time actually, but in the time series fashions it seems to work. At least it's not making it worse. And our conclusion is, for the weak atmospheric condition or scenarios, basically all the Sentinel-1 descending tracks and the Sentinel-1 ascending tracks in the middle latitude, not, for example, not in the equators or not in the polar regions. For C-band Sentinel-1, it works relatively well. We're achieving a similar accuracy as the state-of-the-art split spectrum method. But for L-band and for C-band Sentinel-1 ascending track in the strong atmospheric regions, for example, we tested in northern Chile, where the atmosphere is really strong, it's not working well. And so that's depends on where. And all the L-band data that we tested with ALOS2, it does not work because the resolution is too big. And in InSAR, we cares about the spatial variation within our SAR sims more than the co-registration.
Yeah, for NISAR interferogram processing, they use the overall TEC file to do an overall shift, but then they do a cross correlation between the two scenes to estimate additional azimuth and range offsets to get a good coherent interferogram for L-band.
That makes sense. Yeah, so right now with this new approach, I don't think it works for directly for L-band, right? That's why I need extra cross correlation for that.
We're coming up to like the end of this session in terms of timing. Do you think, well, how do you
I'm
think
finished.
we're doing? You're done.
I'm done. I'm done. Yeah.
People can make their own interferogram stacks in their own time.
Yeah.
It's going to use up all your disk space. Almost certainly.
Maybe try to use a slightly smaller area of interest. I find with that I find with 4 burst and then reduce the resolution twice. I can use 4 parallels perfectly fine in that larger X large instance. But if you're using maybe 50 bursts, maybe your disk will be full.
Yeah, be careful. Okay. Thanks, Yunjun. This has been great. I look forward to playing with this a lot more. I think we need to take a break. Maybe a 10-minute break. Oh, wow. Need to unspotlight you as well. Do you think 10 minutes would be good?
Melissa, you're gonna set up a timer?
I was waiting for somebody to say yes, that's good. So
It's good.
It's good.
okay.
See you in a little bit. Welcome back, everyone. That's if you did actually come back. I'm staring at a sea of names and no cameras. I'm assuming that there's someone else out there. Oh yes, good, thank you. One person. So the final element of today is going to be a little exercise in modeling, for which I will share my screen. Okay, so hopefully you can see I have my OSL instance open, and we're going to go and look at some notebooks that are in here. I'm going to do the same thing that Yunjun did. I'm going to delete the folder for module 2.2, which is the module we're about to start, because I made some changes to the notebooks yesterday, and I would like you to make sure you have the most recent versions. So you delete that, you hit the button at the top to update, and hopefully in a second we'll re-download those notebooks. Okay, so this module's name is Preparing InSAR Data for Modeling, and really it's a mixture of showing you how different models resolve into line of sight, which of course is the real trick here. We need to understand how the models we might produce of three-dimensional movement are represented in InSAR. And of course, InSAR has its own particular acquisition geometry, it has its particular line of sight, and sometimes the way that three-dimensional motion resolves into InSAR line of sight is not necessarily what you would expect. and it helps to build some intuition towards that. So I have a notebook, for example, this one here called Ocada LOS Components, and I think we should start with this one. Okay, so if you open it, you'll want to run this in the Earthscope InSAR kernel. Otherwise, of course, it will complain that you don't have any of the required installed software dependencies, and we will start by running this first code cell, which imports a bunch of things, and it imports, as you will see, Ocada from a package called Ocada Wrapper, which is basically someone produced an interface to Python to like the original Ocada subroutines. So you run that, and all being well, it should say nothing at all. And then there are some other things that you have to tell. If we're going to make models using the Ocada model of, say, a simple earthquake, then it needs to know things like the elastic structure, the elastic moduli that to use in the calculation, and we're going to use very standard numbers of 30 gigapascals for those two elastic moduli, which are the Lame elastic parameters, or lambda and mu. Anyway, those are standard numbers. And here we can define a few parameters that describe a fault that slips in an earthquake. So, for example, you can give it a strike, which is the orientation of the fault on the map. A strike of 1 degree is basically almost north-south. A dip of 85 degrees, this is the angle that the fault makes with the horizontal. So a dip of 85 degrees is close to vertical. And the third thing you need to tell it, which is the rake, is an angle between the strike direction and the slip direction, which may mean nothing to you at all, but basically it defines which type of earthquake or what type of fault you have. And values of close to 0 or close to 180 are what we would call strike slip faults, where the slip is in the same direction or parallel to the strike. Rakes of close to 0 are left lateral faults that slip to the left. As you look across them, faults with a rake of 180 would be right lateral, slip to the right as you look across them. Anyway, we're going to have a left lateral fault. We're going to put 2 meters of slip on it. We're going to have a fault that is 15 kilometers long and 10 kilometers down dip, so 10 kilometers wide, with a centroid depth, which is the depth to the center of the fault, of 6,000 meters. So the center of the fault is 6 kilometers down. And you can also give it a coordinate in x and y. I'm going to put that at 0, 0. Okay, anyway, these numbers define the shape of the fault, its orientation, its depth, its dimensions, and how much slip it has and in which direction. So there are 9 numbers that define an earthquake in this scheme. And we're using Ocada's model. I mentioned this yesterday, and it's the kind of the classic elastic dislocation model for a rectangular element, a rectangular dislocation, in this case just a rectangular discontinuity in the subsurface, and you can have it be a fault that slips, or you can have it be a dike that opens or closes, or a sill, even a horizontal surface that opens or closes. Those are all possible with this model, and this link here takes you to the paper if you're curious. Oh, it's taking me away from my notebook. Marvelous. Luckily, we can come back. But anyway, yes, if you want to read the paper, it's full of equations and things. You can open that link in a different window. There's also a web page, which again is taking me away from my notebook, which actually was where this figure came from. Contains the links to the actual Fortran code that was originally produced for this paper, and this figure here describes all the things you need to know and all the things I had to account for when actually trying to calculate the Ocada model in a notebook. You need to know that there is a point on the fault, which is the origin of the coordinate system. That the strike of the fault is aligned to the x-axis. That there are these 3 components of motion that you can describe for the surfaces bounding this rectangle. One in the direction of the x direction, which is strike slip. One in the up dip direction, and one in the perpendicular direction, which would be opening or closing. Anyway, I don't belabor the point or go through this in detail. You can go and try and understand what I did, but basically I made an implementation of this code with this geometry for real coordinates, and I made assumptions like that this origin would be at the center of the fault, and I had to define some rotation matrices and things to convert between this coordinate system with the fault aligned with one of the axes and real coordinates where it might not be. Anyway, let's not worry too much about any of that. Did I have to run these in sequence, huh? Because I left the notebook a couple of times after rerun the first element. Okay. Anyway, so these calculations will just calculate the displacement field associated with the fault I just told you about, which is basically north, south, and vertical, close to. And all this setup just does all the calculations to figure out the coordinate system and how this fault sits within it. Here, I actually run it, and you'll see what I've done. I've made a linear space, which is the coordinate system I'm going to calculate displacements on, between minus 25,000 meters and plus 25,000 meters in both x and y. I'm dividing that into 101 elements, 50 kilometers, 101 elements. I think my elements are 500 meters each. Don't quote my math on that. I make some arrays to store the outputs, and then actually running Ocado, you just loop through the rows and columns where you're trying to calculate the displacements, and you evaluate the model at all of them. And then you rotate the coordinates into the coordinate system, and at the end of it all, you get some output. Okay, so when you run this, this north-south fault produces the following displacements in x, y, and z. So there's a fairly large north-south component, because the fault I'm particularly choosing to use is a north-south fault, and it's slipping in the direction that's parallel to strike. So you get a very large north-south component of motion when you do that. But there are secondary and not insignificant displacements in the other two coordinate directions as well. There's a fairly large horizontal displacement in the east-west direction, which is shown here. And also there are displacements at the ends of the fault in the vertical component, shown here. So the fault runs basically from the center of here to the center of there, if you can see my mouse pointer. And at the ends of the fault, where you go transition from a fault that's moving to an area that it is not moving, you'll either squeeze vertically the end of the fault, or you'll stretch it, and so you get this coupled uplift and subsidence at the ends of the fault, which is shown there. I spent all my time mentioning this because if you remember anything about the geometry of an InSAR image, you'll probably remember that the faults are flying almost north-south, and they're looking usually, in the case of Sentinel-1 anyway, to the east, and in the east-west direction and down, which means, of course, that they are really not very sensitive to the displacement in the north-south direction. So even though that is the largest component of motion that you would calculate with the model, it may not be that well represented in the deformation field, and we'll show you that in a minute. There is a question that can I show the formulas used for Ocado, and absolutely not. You should go look at the paper. I've given you the paper to read. You'll see that some of the equations in the paper are in landscape, and they fill one column. There is absolutely no way that anyone could remember those equations, and they are coded into a subroutine so that no one has to actually look at them. I did once translate the Fortran subroutine into MATLAB on my own, and that took most of a day. It's not something that you would look at lightly. So no, I'm not going to show you. But you can look at the paper yourself and decide whether or not you want to see it. It's not nearly as simple as like MOGI, where you have two equations that you can evaluate. very, very quickly. That's why it's set up where it calls this thing called DC3D wrapper, which is part of this Okada wrapper package. That's a subroutine that will calculate displacement based on the numbers you feed it. There are 9 input parameters, remember, so of course it's complicated. Anyway, what I want to do instead is spend my time trying to project this into something that looks like the geometry of an interferogram. And so to do that, you actually have to calculate the line of sight vector. And depending on how you define the angles, Yunjin already spent some time showing us the incidence and the pointing azimuth angles. We use those numbers in this subroutine also, in this notebook, to calculate the expected sensitivity of the deformation field in X, Y, and Z to the model displacements. So yeah, if you use the definition of pointing vector that ICE uses, then the 2 angles that you measure, one of which is the pointing azimuth, so the direction that the satellite, the ground target points towards the satellite at. So the reverse really of the pointing direct vector from the satellite to the ground, from the ground to the satellite. That is given by the angle phi or phi here, and then the incidence angle, which is the angle that the incident radar makes with the ground, where incidence of 0 would be vertically incident, and incidence of 90 would be horizontally incident, which of course never happens. But normally this angle for Sentinel-1 is between about 30 degrees and 46 degrees, so somewhere in that range. Anyway, the X component, the Y component, and the Z component of the pointing vector, the unit pointing vector components, are given by these 3 expressions here. So you can see that this is in range changed convention, because the cosine of the incidence angle as the vertical component has a negative sign, which means the radar is pointing vertically downwards. And if it was the other convention, you would multiply all these things by -1, and you would have the vertical sensitivity would have a positive sign. Okay, so whatever I'm going to show you is in range change, not in ground displacement. And you can pick your angles that you can use. You have a choice of incidence angle. So 39 degrees is pretty much the middle of the Sentinel-1 swath. That's the kind of some representative angle close to the middle of Sentinel-1's swath. And the pointing azimuth angle is -260 degrees, which, okay, that's 260 degrees counterclockwise. You could just add 360 degrees to that, and it would have an angle of about 100, which is what Yunjin was showing earlier. I don't know why ICE2, which is where this numbers came from, like to use negative angles, but anyway, you can evaluate the trig anyway for these angles specified here, and you'll get some pointing vector component. And for the numbers I used, this is the output you get. You get an X component, which is as an amplitude of 0.61 or 0.62 positive, which means that the satellite is going to be pointing to the east. You have a Y component, which is 0.1, which means it's pointing very slightly north. And then the third component here, the Z component, is it's pointing very slightly, well, pointing at 0.7 degrees, almost 0.8 degrees down. So you see that of the 3 components, the X component and the Z component are the largest in amplitude, and the Y component is pretty small. Okay, So anyway, the next thing that what happens is we take these three components, and we're just going to assume for now that the line of sight vector is fixed across the whole image, which isn't true in detail, but over short distances it's maybe defensible. And we're going to project these three sets of displacements into the radar line of sight and add them together, and that would be approximately what you would see with InSAR. Okay, so all this does is literally multiply each of the three displacement components with the three vector components, and then we add them up, and then we plot them. Okay, so what do you get? When you scale the three lines of sight components, remember that the Y component was large and the X and Z were significantly smaller. When you scale them by their contribution to line of sight, the Y component goes to almost nothing because we're very insensitive to it. But the X and Z components, those still contribute to line of sight displacement. And in an interesting turn of events, if you look at how they are organized, okay, so in the X component you have positive in the north and negative in the south, and in the Z component you have alternating positive and negative, negative and positive. When you add these two things together, they partially cancel on the east side of the fault. So you get almost no displacement in the sum over here because you're adding this positive to this negative, and over here where you have negative and positive in the vertical, when you add those together they cancel too. And on the other side of the fault they add up, so positive adds to positive, negative adds to negative. In the end you end up with a very lopsided looking interferogram, which does not look like anything I think you would have expected. And the first time I saw an interferogram of an earthquake on a north-south fault, I had to make models like this to convince myself that it wasn't a mistake somehow, that I'd done something wrong. No, actually, this is what you would expect. It's just you have to like realize that you're going to get these weird cancellations of some of the deformation pattern, and maybe these also superpositions of them. Yeah, so you can. So that's what you get for one interferogram. If you change the incidence angle to look at the other interferogram you could make, the descending interferogram rather than the ascending interferogram, you can rerun this again, and now what happens is that instead of having a positive eastward component of sensitivity in the pointing vector, now it's negative. So now you're looking to the west, not to the east. The other two components stay the same because the angles are the same. But this simple thing of reversing the east component of motion, when you calculate what it does to the interferogram, reverses with the side where all the displacement happens in the interferogram. So now you have negative in the north and positive in the south, and when you add that to the Z component, now your interferogram is kind of lopsided on the other side. So this is something that you would expect to see actually approximately in an interferogram, that you will get a change in displacement when you change the line of sight direction, but perhaps you might not have expected it to happen quite this way a priori. But yes, this is what you expect to see if you have a north-south fault being observed by an earthquake, a satellite which is in a polar orbit, where basically its orbital pattern is very close to north-south itself.
Like
Megan
the BAM
asked.
earthquake.
Sorry?
It's like the BAM earthquake.
It's very much like the BAM earthquake. I got very excited yesterday when Molly showed the interferogram of the BAM earthquake, because that came from my PhD and work that I did with Eric, actually, which is why he brings it up. And that's why I made these models in the first place of this type, because, yes, the BAM earthquake confused us a little bit, like, why are we getting all of the deformation on one side of the fault? Well, yeah, and that's a consequence of the viewing geometry of a radar satellite. So Negan asks, is this pattern of line of sight displacement to be seen for all left lateral faults? No, for all north-south faults that are left lateral. Of course, you don't have to take my word for it. You can change the change the inputs here and change the strike of the fault to something which is maybe a bit different. Maybe we'll make it 91 degrees, not 1 degrees. That will make the fault strike east-west. If I run that, then you have to rerun all the other code cells to recompute the model. Now we get all the displacements happening in the east-west direction and very much smaller displacements in the north-south direction. When you factor that into your line of sight components, now your X component contributes a large amount to the phase, and the Y component still contributes very little. The vertical component is small compared to the east-west component, and your interferogram now is mostly aligned with the orientation of the fault, and you see positive displacements on one side of the fault and negative displacements on the other side of the fault. So yes, one of the reasons I made this notebook is that you can actually play with different fault geometries and see what they do. And you can change the rake angle. If you made it negative 90 degrees, then this would be a normal fault, and it would have a very different deformation pattern. Yeah, so you could do that too. Why not? Do it. I can say you could try, but I can also just do it myself, right? Minus 90 is going to change the deformation pattern again in ways which are pretty substantial. Okay, now we have very big, well, I have to change my color scheme. Somewhere in here I can make the axis element values different. Let's see, -1 to 1 maybe. Oops, not bad. Shift enter. All right, now for a normal fault, oh, I made it was vertical, so maybe I need to change the change the dip as well. Change that to 65 degrees. So I'm just making up as I go along, but you can try all sorts of things and see what they do. Okay, here is a fault which has now got a large vertical displacement in the hanging wall, just like we saw for the Dino earthquake yesterday. Big subsidence in the vertical signal. Some things in the east and north which are small compared to the vertical, which is why, of course, yesterday we assumed that all the motion was vertical. And when you run that through, I'm going to have to change the downs on this plot as well. Don't mind me. Now your interferogram is mostly dominated by the vertical, and you can see here most of the deformation is range increase in the earthquake hanging wall, like we saw yesterday. Right, there are questions. Why does the contour line for the line of sight displacement in the descending track have more contour lines along the positive displacement compared to the ascending track? It's going to be something to do probably with that very small, could be to do with that very small north-south component actually adding enough displacement to give you an extra contour, I'm guessing. Something like that. It's not a very, very big effect though. But it's an exact calculation, so you could actually look at the numbers if you wanted and try and figure out that. Please, could you use these values? No, why don't you do it? You could do it and show us if you prefer. I'm happy to let you show me a model of a different earthquake if you want. But yeah, I don't think I necessarily need to do it for you. I think you can do it. So, Rodrigo, if you want to show us this earthquake, please do. And I'll take the opportunity to choose a different notebook while you're not looking. So, Rodrigo, are you doing this? Show signs of life if you are. Give you 30 seconds to tell me that you're going to do something and show us. Otherwise, we'll move on. Is anybody there? Am I talking to myself? Other people are there. Okay. Well, he had his shot. Too bad. Too late. Just to say, there is another notebook that I have, which is very similar to this one, the one I just showed you, which is called How Displacements Resolve into Ascending and Descending Line of Sight. And so really it does exactly the same calculation that I was showing you before, but instead of doing them one at a time, it calculates both ascending and descending together. So if I run this one, whoa, I'm using the wrong environment. Okay, let's go InSAR. Right, it couldn't find Akada because in the base environment, Akada is not installed. You run that, off it goes. Here you can feed it some fault parameters. Pick your favorite ones. Again, this is a north-south fault. This one is right lateral. This is very similar to the BAM earthquake, actually. And then it does the calculation as before and does all the projection and calculation all in one go. So if you wanted to look at all the things next to each other, this is what you get. So you get your X displacements, your Y displacements, and your Z displacements like before. Like before, the Y is the largest, the X and the Z are small, but when you scale them by their contributions to line of sight for ascending and descending, you see that the Y component goes away and the X and the Z are what control the pattern that you get. So yes, if you wanted to play with this one and type in your random earthquake of choice, you would be able to see what it does to the deformation field and what the expected ascending and descending Sentinel-1 interferograms would look like. Perhaps for your own edification and interest, you might consider how to modify this code to produce the same quantities, but for NISAR. That would be about 10 degrees different from, for example, if you had the pointing vector, I think for ascending Sentinel-1 is 100 degrees from the ground to the satellite. It would be probably 10 degrees the other side of east-west for NISAR, so it would probably be 80. And you could see what happens to the deformation field. It will reverse the north component a little bit, but the sensitivity of east-west and vertical will be very similar. And that reversal in the direction of the north-south component of motion and how it resolves into the satellite line of sight is actually why some people are very excited to compare NISAR data to Sentinel-1, because it's got a different sensitivity to north-south motion. You might actually be able to solve for the north-south displacement by comparing Sentinel and NISAR data. If you have like 2 Sentinel interferograms and 1 or 2 NISAR interferograms, you should be able to resolve all 3 components of motion, which would be exciting. You can make a version of this notebook.
The azimuth is exactly 180 degrees different from the same from the Sentinel-1. So the ascending would be minus 260 plus 180, or
right. Yeah, I mean, it's an easy calculation to make. And yeah, you could modify this notebook to show all 4, Sentinel-1 and NISAR, for the same earthquake. Maybe I should do that sometime, but maybe you could do it too, because it's not actually that conceptually difficult. You just copy the code cell and copy maybe the one where you calculate the line of sight vectors, which is here.
Because it's on the opposite side, the ascending Sentinel-1 looks like the descending NISAR, and
right,
vice versa.
With a very small north-south component difference. Yeah.
Yeah.
Okay. So resolving for north-south is coming from the left-looking capabilities of NISAR. Yes, actually, that is part of it. So someone asked earlier this morning why NISAR was going to be left-looking, and there were really 2 reasons. One is that it gives better coverage of Antarctica, the left-looking geometry. and our friends who do cryosphere things were very excited about that. But the people who do tectonic things were very excited about the possibility of comparing right and left looking interferograms and solving for the north-south component of motion. So yes, that wasn't a downside to us, that it wasn't going to be a right-looking satellite. And in the future, there will be a right-looking L-band satellite operated by the European Space Agency called Roselle, which will have very similar acquisition plans to Sentinel-1, which is to say you'll get 12-day coverage potentially, ascending and descending in L-band right-looking. So the combination of all these things together is going to be amazing for that. And Stephen has been trying to calculate what the sensitivity is, which is cool too. Okay, so I've answered these. Okay, anyway, so that's just a primer for really understanding how we need to take very good care to resolve the line of sight information when and use it when we're modeling earthquakes. You can't just assume necessarily that all the deformation is going to be east-west or vertical. I did show you an example where for a normal faulting earthquake with a steep incidence, it is very close to vertical, but not exactly. And if you want to make an exact model, then yes, you need to take line of sight into account. All right, so that's one thing. That's part one of this module. Okay, what's this question say here? I'm still trying to understand what the Z component looks like it is. It's because the fault is finite in all of these cases. The fault comes to an end. So when you travel from the end of the fault, which is slipping, to the part next to the fault, which isn't, there is going to be a push or a pull on the immediately adjacent part of the crust, and it will either squeeze the crust and cause it to uplift a little bit, or it will stretch the crust and cause it to subside a little bit elastically. And that's why you see that pattern of little uplifts and subsidences at the ends of the fault segment, because you're getting this pairing of squeezing and stretching right next to each other.
Also, like a follow-up question on that. So in the reality, we don't see this pattern that significant because the faults are like not that abrupt stopping at that
Right.
point. Is it the reason? Okay.
That would be part of it, except we do see this pattern in interferograms. So it's not that abrupt. It's less abrupt than it's represented here, but it might taper a little bit. But we do see this sort of pattern, even so. As I said, like this earthquake in Iran, the BAM earthquake, it really does have displacements that are quite sharp like that. Let me see if I can find it actually. Find paper somewhere. 2005. My goodness, it was a long time ago. Let's see. Let me find my interferograms. They are, yeah. Right. So this is a real case where the whole deformation field did just reverse like that, and you do see these areas, which are basically the areas of uplift and subsidence, on both sides of the fault, flipping between ascending and descending patterns. So it's not fancifully made up. It really does happen in nature. All right.
Okay, that's very interesting. Yeah.
Yeah, read it, cite it. It's great. Eric and I both get a citation if you cite that paper. Okay, so that was the first thing we wanted to talk about, was the importance of line of sight. I think maybe we understand that, or get the point. The next thing is data downsampling. So we've talked a little bit, and we've done an exercise already where you've modeled a MOGI source, and that MOGI source was evaluated over the whole interferogram. And yes, you can do that, and yes, we did do that, but perhaps it's not the most efficient computationally way to calculate a model. Instead, because the data are so spatially correlated, areas far away from the fault don't really slip very much, and they slip very similarly to the pixels around them. You could downsample the data, which is to say average it spatially over some length scale, and you don't really lose much information, but you do gain faster computation when you do that. So what I have here is a notebook that applies a very common downsampling approach, which is called a quad-tree decomposition, and I would just demo it. I'm not going to go really deep into the weeds and how it works or anything, but I'll show you. So anyway, we import the dependencies. This here is a code cell that downloads an interferogram processed using ISCE2, but anyway, it contains much of the same sorts of information. This felt top of phase.unw file is the unwrapped interferogram. It comes with it as a two-layer file with the amplitude of the interferogram and the phase of the interferogram embedded in it. This is the line of sight information with both the incidence and the azimuth angles embedded in that. I have a water mask, and we have the coherence, or rather the correlation, which is the complex correlation, not the phase sigma, although ISCE2 does produce both of those. Here we have the file name set up, just naming where everything is. I downloaded it to the directory you're in, so the path to the files is // for here. Anyway, those are the files. Here is some more additional information. I'm going to say we would like to specify a wavelength for the radar. 0.0555 is the actual wavelength of Sentinel-1. And yes, you can specify a correlation threshold for like things to zero out that are low correlation. That's pretty low, actually. I think less than 0.25 is going to be a bad pixel. And then we load in the data, and maybe it will plot. Here is an interferogram. This is in radians here. We load in some other information. We load in the correlation file. We load in the line of sight information. We load in the mask. And here we'll convert the interferogram from phase to displacement. So we'll take the wavelength, we'll multiply by the wavelength and divide by 4pi. And we mask out low coherence pixels. And somewhere else here we also apply a water mask. So if you do all those things, hopefully this doesn't complain, then we can see what we've done to the data, having masked out the water and the low coherence pixels and also converted it to displacement. Now you can see these are in displacements in meters. Okay. The next thing we do is we apply the quad-tree decomposition, and what this does is it takes an area of the interferogram and calculates the variance of the phase within that area, and if that variance is above a threshold that we specify, then it will divide it into 4 smaller areas and then repeat the process. So what this does is if there's a large variance in an area that you're looking at, it will keep subdividing it until you have a small pixel that captures basically that information about that type of motion. But if you're far away from the fault and there's very little variation in the data, it doesn't divide the area at all, and you can specify a maximum block size and it will keep that. Okay, so here we have, for example, some things like the variance threshold, which is in the units of meters squared. We have a thing that allows it to have a lot of null pixels in a box. You can have 50% null pixels and it won't divide up the box just because it's got null pixels in it. And then in degrees, longitude and latitude, you can specify the maximum block size and the minimum block size, and it will divide up your image according to that. So anyway, when you run this, it will apply that quad-tree decomposition using these parameters, and the first thing you can do is see how many pixels it's divided your image up into. It's 194. Okay, cool. And you can look at where those are and what phase values they have, the average phase or the average displacement within each box, and where the center of the box is in latitude and longitude from the lower left corner. Let's not worry about that. but also you can plot what those downsample blocks look like, and this is what they look like. So you can see, for example, if you're far away from the business end of the earthquake, then there's not much variation here. The blocks are large, the values are all very similar. But once you get close to where the displacement in the earthquake happened, you have a lot of pixels, which are small, which will resolve these different displacements. What's the approach to decide on the initial value of the variance threshold? I would say trial and error. If you want a few, I would say you want a few hundred points. If you find yourself having fewer than that, then you lower the threshold. If you find yourself having too many, then you raise the threshold. That's really how you go about it. For now, I recommend keeping these bounds as I've set them, because we are going to use this data later on to make a model, very later on, like in about 5 minutes. And I would like us to have comparable results, please. So use the same data points. If you use a different set of data points, then when you calculate things like misfit, you're not calculating the same thing anymore, because you're calculating the misfit to a different set of points. Anyway, so it's done the quadtree decomposition. I'm fairly happy with this. And then what remains in this notebook is converting the coordinates from lat long to UTM coordinates, so that we have a rectilinear coordinate system that we can use. That's what this cell does. Hopefully it doesn't complain. It didn't. Okay. And then we export the information from the quadtree, basically the locations of the center points of each of these subdivided cells, along with the representative line of sight information for each of these pixels, which the quadtree code calculates for us. So each of these boxes comes with its own east, north, and up pointing vector. So we want to output that as well. And that is what this set of things does. So in the end, we have a bunch of points in UTM coordinates. I'm going to use UTM kilometers here. You can see X and Y in kilometers. We have locations of points within that XY grid. They have displacements associated with them in meters. And each of these points has a line of sight vector associated with it, and we save that to a file here and here and here. Okay. So at the end of all this, it's made me a file called elazig ascending okinv. Okay, you don't have to worry about that. It's for Arcada inversion purposes. It contains the X and Y coordinates of each point, the displacement of that point in meters, and then here are the 3 line of sight vector components. We need that, of course, to convert between east, north, and up into line of sight. So that is what we have gone and made ourselves. Ryan says, is downsampling appropriate for infrastructure monitoring? Probably not necessary, unless you have particularly large infrastructure that is so noisy you might need to average the pixels together. Probably not. I'm going to say most of the time, if you're studying small targets, you need all the resolution you can get, whereas downsampling is clearly making use of that oversampling that you have to reduce the number of points that you have.
I guess it also depends on what kind of model you have. You want to preserve enough data so that the natural variability that's forecasted by the model is still represented. If you have some sort of an infrastructure model that sort of would forecast small scale displacements based on whatever, like temperature, etc., you have to make sure that you keep enough points close by to actually represent the variability the model would predict.
Yeah, thanks. We're going to move ahead, I think. So I realize I'm short on time. The next notebook is called a CARPI optimization, and a CARPI is just a series of Arcada-based routines written in Python. it's its own little Python script here, which you can look at if you want later on. It basically does the calculation I showed you in a notebook before, but it kind of hides it, so you don't have to look at big code cells where it's doing rotations and coordinate transforms and all that stuff. Anyway, we're going to import that. We're going to import some math and some other things. We're going to import some SciPy optimization routines. So we're actually going to try and model this earthquake using nonlinear optimization and some plotting. Okay. Whoa. Always remember to use the right kernel. So when I do that, it's not going to complain. Good. So the first thing that happens here is we load in the data file that we just made with the quad tree decomposition. No problems there. The next thing we're going to do is we're going to guess some model parameters for this earthquake that happened in Turkey. Yunjin already pointed out, at the end of his notebook had a link to the USGS webpage for this earthquake. You can go look. Of course, we also have the interferogram where you can eyeball approximately what the fault might have done. So for example, here we can guess things like the length of the fault based on the length of the pattern here, probably from about there to about there, somewhere in the realm of 30 to 40 kilometers. We could estimate what that angle is for the strike. The strike is probably about 60 degrees. That would be the angle between that sort of trend and north. You can guess things like the depth of the fault, and the dip could be vertical, don't know. That would be my starting guess though. So that's what I've done here. I've given guesses for the various parameters like the strike of the fault, 60 degrees. And I give an uncertainty, which is a 1 sigma uncertainty. So we could, if we allow things to vary between 2 sigmas, the bounds of that we place on the inversion will be basically double these numbers. So I'm guessing it's 10 degrees strike. I'm guessing it's somewhere close to vertical, plus or minus 30 degrees. So dipping north or south, don't really know. The rake I'm going to assume is left lateral because the East Anatolian fault is left lateral that this earthquake happened on, but I'll give it a big uncertainty there. I'll let the slip vary a lot as well. And I guessed a location for the center of the fault about here somewhere. I said 500 degrees, okay, 500 kilometers for the X coordinate, and I don't know, 42 something in there for the Y, 4240. All right, cool. I guess the length is 35 kilometers plus or minus 10. Top and bottom depth, that was complete guesswork, but trial and error. You can refine these if you don't like them. But anyway, I think these work. And I make vectors out of these. So you can see that all these numbers get sort of compiled into one string, and their uncertainties do as well. And then I calculate what the bounds would be based on those sigmas, assuming that plus or minus 2 sigma, okay, whatever. And then I pick a random number from within all these bounds as our starting model. The way that these optimization algorithms work, and I think Franz mentioned this already today, is you have a starting guess for your solution, and then your algorithm plays around with the model parameters and say, okay, if I change this parameter, does it make the fit better or worse? And if it makes the fit better, then it keeps changing that parameter until it doesn't improve anymore. Then it tries to change another one. And overall, as time goes on, if I'm showing a downward motion, it's because you would imagine a plot of misfit. Imagine those XY plots that you made before of the volume versus the depth for that Mogi source. That basically you're trying to find the lowest misfit. So like these so-called downhill methods try to find the way to the bottom of a plot like that. That's what we're doing, except we're doing this with 9 parameters. So this is a 9-dimensional space. I don't think very well in 9 dimensions, but anyway, it's a similar problem, but it has many more dimensions. And if I haven't lost you talking about that, that's great. And then there's a few other things that happen here. If it turns out that your fault is your random selected model has the top of the fault above the bottom of the fault, then it's the bottom of the fault above the top of the fault. It switches them and it writes out your model guess parameters. So here they are: strike, dip, rate, whatever, a bunch of things. Okay, this is just telling Ocado the elastic parameters. We use the same ones that I showed you before, 30 gigapascals. And the first thing we can do is calculate the penalty, which is to say, if you use all these parameters to estimate a model geometry, then you can calculate the expected displacements in line of sight for all the pixels that you're using, and you can compare those expected displacements to the real ones and difference them, and you can calculate a misfit statistic based on that. Basically, the difference between the predicted model and the actual data squared, so that always gives you a positive number, will give you a penalty value. So for my initial model, my penalty is 0.315 meters squared, which is not awful, but it's not great. But yes, values between fractions of 1 and low single digits are very common for this. So if you do it yourself, because it's chosen at random, you'll get a randomly good or bad model from the drop. But anyway, that's just our starting location for the starting model. What we hope to see is that when we run one optimization where it runs the algorithm and it plays with all the parameters, that you will find a model that has a better misfit than the one you started with. Okay, so that's the goal. We're going to do that, and we're going to run this algorithm. The specific algorithm we're going to run is called a Powell algorithm. It's a direction set downhill method. If that doesn't mean anything to you, it's okay, but it basically does what I've been describing. It chooses one parameter, then another one, and eventually it starts searching in the directions of multiple of these parameters together and tries to find the best directions to go and vary the parameters by until it finds the minimum. So I'm going to run that, and it's not going to take very long, but it's going to chug away, and it's going to run a bunch of forward models. It's going to tweak them, then rerun them, and tweak them, and rerun them, and tweak them, and rerun them. It's already done. That's good. Okay, it's successfully finished. It gives me a penalty function, which is this fun thing here of 0.09. Compare that to my initial function of 0.315, so it's better. It's fit slightly better. These parameters here are the ones in this kind of string of numbers that I made somewhere up here. Yeah, I made put them all in this string, so they're in this order: strike, dip, rake, slip, x, y, length, depth, or length, top and bottom. That's what these numbers represent. It changed direction 19 times, and it ran the Ocado calculation 3,346 times. So it's not a very computationally efficient model, but because it's analytical and it's fast, it ran pretty quickly. And you want to read, if you want to interpret what it gave us, this here will just print them out. So the strike is 59 degrees, the dip is 102, which means it's dipping. If dip is to the right, strike is 60 degrees, it's dipping north, okay, at about 78 degrees to the north. The rake is almost left lateral, slip is 1.5 meters. It gives you a location of the fault and the length and the top and the bottom depth. And yeah, okay, the penalty got better. Right, so you can take these numbers and copy them. I had a space where I could secrete these. Oh yeah, here. Best fault parameters so far. These are my best ones, and you can turn them into a Python NumPy vector like that. And I can copy my penalty value as well and paste that here. All right.
You'll have to do what Gareth just did to make the next code cell work.
Yeah. So yeah, you find your first model. Now we already mentioned, of course, that we have to have a starting location, a starting guess, in order to run this modeling approach, and it's often the case that maybe that's not the best starting model. Different solutions will come from different starting locations. So if you're going to do this type of modeling seriously, you want to have a lot of different randomized starting locations and then try a lot of different models. What I've discovered is what we call a local minimum. It's the best fitting model for the starting location that I had, but it could be that there is a better one somewhere else that started in a different place. In this in the text here, I describe maybe if you're trying to find the bottom of the deepest crater on the moon, and you just have a process where you walk downhill until you get to the bottom of something and then stop, then of course, if there's a bigger crater behind the crater in front of you, you might never get there from your starting location. So you should try this from a bunch of different places, and eventually you will find your way to the bottom of the deepest crater. And in this case, the craters are our penalty function that are misfit, just like you had a valley for the Mogi inversion that you were doing. Anyway, you can. So with that in mind, because I've asked lots of you to run this, lots of you are going to have penalty models from different random starting locations, and what we can do is maybe compile all those. So I've made this notebook, this spreadsheet that I need the chat. I put the URL of this spreadsheet in the chat. Will it actually let me share it? No, hang on. Share, copy link. Done. There. Okay. Remember, I said that you want to start from lots of different starting locations. Well, because I got about 100 of you on here, and normally we would run this 100 times ourselves, I have gone to the trouble, because you all run it, you could all have a solution from a different starting location at random. So please pick a line that no one else is using, type your name in to bag that row, and then paste in your penalty value and the string of model parameters, and populate this spreadsheet. That would be great.
Happening! Holy crap!
It is happening. Be careful not to take up multiple lines with your parameter string. You're going to have to delete make sure they're all on one line. Otherwise, you'll mess with other people's. So, like for example, Kira, yours are spread out over 3 lines. Yeah, you'll figure it out. In the meantime, you can see what the model looks like that you've got yourself by running the next code cell here. So if once you've did I forget a comma? Yes, I did. There's one missing here. Oops. Right. Oh man, I've got to put commas in all of them. That's right. My bad. I can do that though. This evaluates the model with the parameters that I gave it. It shows you the data, the prediction from the model, and then the residual, which is the difference between the two. And looking at this, it's not too bad. It fits the data quite well. Yes, it doesn't quite capture all the features. There seem to be 2 lobes of deformation, and this fault model is only going to give you 1. So we're only using 1 fault, but it's not too bad. We come back to the spreadsheet. How's that getting along? We're going to give you a few minutes maybe to get your results in here. There are, how many of you online right now? 97. We could have up to 97 different versions of this. I can add mine, I suppose. Give me a second. I'm going to bag my line down here. Oh. Gonna get my best parameters.
Don't forget to also add your parameters, especially if you feel like you're very competitive. There's at least one person, Seamus, I think if you add your parameters, then people could try them. You seem to be very close to the best.
Yeah, once everyone's are in, we can nominate some Excel whiz to like sort the spreadsheet by penalty, and we'll find whose models are the best.
Awesome, thank you.
Seamus is looking competitive there with point.
Yeah, I think that. Oops, what just happened?
Someone's doing some sorting. Could you wait a little bit longer? I think for like people to get their numbers in. We'll give you. I don't know. Do you want to count? Someone want to? We'll give you a minute. All right. I think the activity is
slowly dying down.
Yeah. Some people did the wrong thing and ran the last notebook cell, which tries to do this optimization without the crowdsourcing. Yes, of course, if you want to run 100 times yourself, it's going to take ages. Whereas one time amongst 100 people doesn't take very long at all. Okay. Could someone sort this by penalty, please? We have a volunteer. Maybe stick your hand up. There you go. Ooh. So the best penalty.
It's a pretty tight race.
Ganirat. I see. Here. Could be the winner by down in the sort of the fifth or sixth decimal place. But this looks like the best parameter string. Okay, let's take that. Let's go back here and replace the best parameters with those. You could paste the penalties, maybe less important because it doesn't use that in the model, but we can also copy that. Why not? This is the prize-winning model. It does look pretty nice, actually. It does a pretty good job of fitting. I mean, I think you might be hard-pressed to tell a very dramatic improvement from the one I had, but statistically, this is better. And this is how you go about it. Basically, you would run the model a bunch of times, and the one with the best misfit is the best model. As I mentioned, there is another code cell down here where actually it will run this modeling approach 100 times, and it will save the best misfit as it goes along, and we'll come up with an answer at the end. So if you want to do this yourself, that's probably what I would advise, because you see there is a big range of starting parameters and a big range of where you end up, and you would want to test a bunch of models. But I would be very surprised if you got a very improved fit to the data running this than we just got, because basically this was very close to like the best model you could get for this setup, I think. Anyway, that's what we that's how we do this. That's the kind of the general philosophy for how we go about modeling these things. We figure out how models resolve into line of sight. We downsample our data, and then we make an optimization model that tries to find the best model geometry using a nonlinear optimization. So that was a lot. We are a few minutes over. My bad. I figured this might happen. I'm sorry. But we have homeworks for you today. Yunjin already mentioned the first one, which is to process your own interferogram. A location of your own choice using his ICE3 notebook. You can save the final interferogram as an image and upload it to Moodle as the proof that you did it. The other homework is to model a different earthquake using this approach. You take the interferogram, you downsample it, you run an optimization on it. There are a few choices of what you can do here. One is I've provided some instructions which you can follow for how you could download a different interferogram that's already processed for a different earthquake and get the data for that. Of course, if you're feeling particularly keen, then you could process an earthquake using Yunjin's approach and then import that into the quad tree decomposition and then use that as your earthquake you can model. If you want to do that, you will notice in the quad tree notebook, if you go back up somewhere towards the top here, that there is this whole section here commented out right now, which is my first attempt to use a Yunjin style ICE3 interferogram in this quad tree decomposition. So as it's currently set up, this is going to give you the interferogram that you just processed of Hawaii, which is not an earthquake. So I don't think you should use this to model an earthquake, but you can, when you process your own data, you give the path to the files on the system, it will find them and it will do that. Someone says the minimum magnitude earthquake. I would say magnitude 6 earthquakes are good targets. 6 or larger on land within the top 20 kilometers of the crust. So yeah, you're likely to see those. Anything a bit
Eric,
smaller,
do you know?
It can be hit or miss.
Eric, if you're still on, so NISAR has an urgent response mode that sort of is activated for earthquakes that meet certain criteria. Do you know what those are, Eric?
Yeah. It's the NISAR urgent response is set to magnitude 7 in United States and in and near the United States and India. But then the other main criteria is based on the pager, USGS pager estimate of damage and impacts. So for global earthquakes, it's pager level orange and red, and for the United States, it's pager level yellow.
And Gareth, there's a follow-up question. Oh, you closed it. Okay.
Yeah, I was going to say, of course, yes, now you know what a north-south earthquake looks like. If it's on a strike-slip fault, it'll be a funny pattern. If it's on a dip-slip fault, it will look very, very standard and very easy to identify, probably. But yes, you can do that. Well, at the moment, I have not built the capability of reading in NISAR interferograms into this notebook. I plan to do that this week because I have been looking at an earthquake with NISAR data in Northern California. It's right on the limit of what you can see. But yes, I think we will wait until tomorrow, and we've actually gone through some notebooks that show how to apply corrections to NISAR data before I figure out how to ingest those into this notebook. I fear if you didn't apply the ionosphere correction to a NISAR interferogram, you just quad tree it based on the ionosphere, which is not the signal you're looking for. Anyway, that should be enough for you to be getting on with.
Any last minute questions?
Yeah.
If that's not
in 3 hours.
Yeah, we have a what is it, like 5 p.m. Pacific office hour. So if you want to start on your homework and it's convenient for your time zone, please drop by and show your stuff or ask questions about it.
Yeah, maybe we could workshop this with you because probably we want to try processing some interferograms ourselves.
And otherwise, thank you for all your participation today. And we see some of you tonight at 5 and some of you tomorrow at 7 a.m. Pacific. And then again in the main session tomorrow at 10 Pacific.
Thanks
Good to see
everyone
you
for
all.
coming. See you tomorrow.